friends. My name is Iris and this is CPP in Pajamas. Thank you for joining. Today we will solve question 420 on LeetCode, Strong Password Checker. Based on acceptance rate, this is one of LeetCode's hardest questions, but we will walk through it in a structured manner to make it clear. Then we will solve it such that it beats 100% in runtime. Let us begin. Strong password checker. A password is considered strong if the below conditions are all met. It has at least 6 characters and at most 20 characters. It contains at least one lowercase letter, at least one uppercase letter, and at least one digit. It does not contain 3 repeating characters in a row. For example, here we have the lowercase a in a row, so it's a weak password. Here we have broken this sequence with a B, so we don't have any 3 characters that are the same in a row, so it's okay, it's a strong password. Given a string password, return the minimum number of steps required to make password strong. If password is already strong, return 0. In one step you can insert one character to password, delete one character from password, or replace one character of password with another character. Let us look at examples. Here, password is just a single character, lowercase a. So what are the problems here? Well, 5 characters are missing to reach the minimum length. Also, 2 of the mandatory types are missing. Where is uppercase? Where is a digit? So, by inserting the 5 characters that are still missing here, we can also cover for the missing types by making sure that 2 of the characters that we insert are a lowercase and a digit. So that would solve all problems. So 5 steps required to make it strong. Here, the password is lowercase, uppercase, and a digit. So all the mandatory types are here, but it's also too short. 3 characters are missing to make it strong, so we need to insert them. 3 steps to make it strong. Here, the password is of good length, between 6 and 20 characters, and we have digits, we have an uppercase, we have a lowercase, so all the mandatory types are here. There is no sequence of 3 or more times of the same letter in a row. We have 3 here together in a row, but just twice, so it's okay. Nothing to fix. It's already strong, so we return 0. Constraints. The password length will be between 1 and 50 characters inclusive. The characters, we will find them, are letters, uppercase, lowercase, digits, dot, and exclamation mark. Here we see the low acceptance rate. Let's understand it and an algorithm on paper and then write the code. My first approach to solving this problem was wrong. What I tried doing was iterate through the entire password, and when I encountered a problem, I just fixed it. When dealing with long passwords, where we need to delete characters, it always turned out that I made a mistake somewhere in deciding whether to delete characters in order to break a sequence or replace characters in order to break a sequence. For example, here, this is a sequence of 5 characters. I can break it with 1 step, or I can break it with 3 steps. Naturally, I choose 1 step because it's less than 3 steps, but it always turned out to be wrong because I do have to delete characters in password that are too long, but where to delete them? In which sequence, and in which sequence to replace? Well, I could never get it right before analyzing the entire password and getting all the information about all the sequences and their lengths. I could never decide before analyzing the entire thing and getting it right. And then I realized that the question doesn't actually ask us to fix the password. I don't really need to do that. All I need to do is analyze all the problems and just state the number of steps. I don't need to actually fix the problems. And that's what we can and should do. We are going to analyze the entire password, know how many sequence breaks there are there, know how many of the mandatory types, lower, upper, and digit, are missing there. Know how many characters are missing or need to be deleted. Just analyze the entire thing and then calculate the minimal number of steps required to fix it by understanding what fixes can cover for several problems at once. For example, here there are 5 characters. So what problems are there here? Well, this password is too short, right? There is 1 character missing. Also, 2 of the mandatory types are missing. Where is the lowercase? Where is the digit? Also, it's a long sequence. Well, if we do this, I both entered a character reaching the minimum length of 6, and also I broke a sequence. And also I got one of the missing type, a digit. 3 problems solved at once by inserting a digit in this strategic place. But then again, we have another sequence here. So by replacing a character here, like so, I made 1 step but solved 2 problems. I got the other missing type, a lowercase, and I broke the sequence. So just 2 fixes covered for many problems. Okay? And this is what we need to do. See what fixes can be made to cover in a single step more than a single problem. Okay, so to do this, we're going to divide the problem into 3 cases. A password that is too short, less than 6 characters, a password of good length, and a password that is too long, more than 20, where we did need to delete some characters. We start here. Let's go quickly through all the cases of passwords that are too short. Well, here we are missing 5 characters and 2 of the 3 mandatory types. Well, we can make sure that 2 of the 5 characters that we enter cover for the 2 missing types, like so. And then we can add just whatever 3 other characters we want. So what determined the number of steps was the number of missing characters, 5, while 2 of them covered for the missing types. Same here. 4 missing characters, 2 missing types. So have the missing characters cover for the missing types. And 2 more to complete to 6. So again, what determined the number of steps was the number of missing characters. Here, again, same as before, but also a sequence. And as we have seen, we can break the sequence by adding the missing characters just in between, like so. This digit solved 3 problems. Added a character out of the 3 that are missing, added a missing type out of the 2 that are missing, and broke the sequence. All that we need to do now is just add 2 more characters, like so. One of them covers for the other missing type and just another one. So again, it's the number of characters that are missing that determine the number of steps. Here, just the same. 2 missing characters, 2 missing types, and a sequence. Solve 3 problems, added a missing character, added a missing type, broke the sequence, and the other missing type. So again, it's the number of missing characters that determine the number of fixes, of steps. Last case, a bit different, because here there is just 1 missing character, but 2 missing types. So I can cover for both missing types by adding a single missing character. So let's do the first, solving 3 problems at once, and for the other missing type, I'll just replace. I can replace either of these, but for symmetry, I'll replace this. So solving 2 problems with 1 step, having the missing type and breaking the sequence. So what determined the number of steps here was not the number of missing characters, but the number of missing types, because it was bigger than the number of missing characters. In all those cases, what didn't matter? Exactly, sequences. Because every time the missing characters and missing types broke the sequences, we didn't need to deal with the sequences as a separate problem. We solved them by having to enter missing characters or missing types. So we can say that at the worst case where all characters are the same, even then, this necessarily means that there are 2 types that are missing, right? If all 5 characters are the same, 2 types are missing. Whatever sequences we'll find in passwords that are too short, the number of missing characters and missing types will surely solve the sequences, surely. So the algorithm for password that is too short is the maximum between missing characters and missing types. Okay, that's the algorithm for the number of steps for a password that is too short. If more missing characters than missing types, then they will cover for the missing types. Otherwise, they will not, like here. Sequences will be broken anyway. Let's move on to passwords of a good length. Before doing that, I'll just show you. I just showed you the worst cases here. If we had simpler cases, like we have all types here. We have no sequences here. Of course, it's the number of missing characters that determines the number of steps. These are simple cases. We looked at the hardest. Okay, so let's keep on looking at the harder cases of password of good length, like this. So what problems are there with passwords of good length? Well, surely we do not need to add characters, we don't need to delete characters. The only problems we may encounter are missing types, like here. We have 2 missing types, and sequences that need to be broken. So, for example, what we will be doing here, I'm not going to insert a character here to cover for the missing type. I'm going to replace. And why is that important? Because if we insert characters, we may get to a password that is too long. If the password was originally of 20 characters, for example, then adding a single character will already make it too long. We're just going to replace. So, replace this with one of the missing types. Replace this with the other missing type. So what determined the number of steps here was the number of missing types. They already broke the sequences. We replaced characters in the sequences by the missing types. But what would happen here? This is still of good length. So we can break this sequence by replacing this with one of the missing type, replacing this with the other missing type, but still there are sequences to break. So we have to have the 3rd step and the 4th step to break them. So what determined the number of steps here was the number of sequence breaks. that we had to do, because the number of missing types could not cover for all of the sequences that we had to break. But you may say, just a minute, why are you saying that you are replacing characters to cover for the missing types? That might cause a problem, because look here. 6 characters, 1 missing type. If you replace one of them with the missing type, you might, by accident, replace this. Losing another mandatory type. Now you don't have a digit. So you need to know where you are replacing. Well, that's not a problem, because as we said, we're not actually changing anything. When we replace, we just say that there is one replacement required. We don't say where. And naturally, if in a password of a good length, if a type is missing, surely, or even if 2 types are missing, surely there is one type with enough occurrences that you can replace and still not lose all occurrences of it. Okay, so what determines the number of steps in a password of a good length, as we have seen, is the maximum between sequence breaks that we have to perform and missing types. Maybe the missing types can cover for all the sequence breaks that we have to perform, but if not, then if there are more sequence breaks, then that's what determines the number of steps. Okay, so let's move on to the third and more complex situation. So this is 6, 12, 18, and that's too long. So we have 24 characters here. We need to delete 4 to reach to the maximum of 20. Also, there are 2 missing types. Also, there are sequences. What's going to determine the number of steps? First of all, we have to delete 4 characters to reach the maximum of 20. We cannot escape deleting 4 characters. What about the missing types? We have to insert the missing types. We cannot escape replacing some of the characters with the missing types. Can replacing characters by missing types and doing the deletions of the extra characters cover for each other? Can we have a single step that both delete characters and replaces characters with missing types? No, we cannot. We cannot do that. We have to both delete characters and replace characters with missing types. Okay, what about sequences? Well, this changes the picture. We can delete characters such that it breaks sequences. For example, let's take a look at this simple sequence. 1 deletion broke the sequence. So we can break sequences by deleting characters. After we delete all the characters that we need to and reach the maximum of 20. For example, here I assume we have 24. I didn't count after the copy paste, but if this is 24, then we delete 4 characters and then we have 20. So already we have 4 steps. To those 4 steps, how many more steps do we need to make? Well, after all the deletions, we have a password of a good length, 20. What determines the number of steps in a password of a good length? This, the maximum of sequence breaks or missing types. This is the number of steps in a password of good length. So after we do the deletions, what we need to do is the maximum between sequence breaks and missing types in the password that is remaining. This gives us the algorithm of number of deletions or let's call it extras, the number of characters that makes it too long because we need to get to 20. So the number of characters that make it too long, the extra characters, plus the maximum between sequence break and missing types that we have after deleting the extra characters, as in a password of good length. What remains to do is understand how the deletions of the extra characters can save us sequence breaks, so that the maximum between sequence breaks and missing types will be the lowest as possible. Well, missing types can be either 0 up to 3, but sequence breaks, we can try to reduce the number of them using the deletions. This is our challenge. Understand how we can eliminate as many sequence breaks as we can using the deletions. Let's do this. Let's examine the different situation of sequences and how deletions can eliminate them. Let's take a look at these examples. Sorry. Here we have a sequence of 3, of 4, and of 5. Let's also have here a sequence of just twice 6, 7. I mean, it's not twice, it's like the next 3, 4, 5, 6, 7, and 8. Okay. So we have 3, 4, and 5, 6, 7, and 8. Let's see the algorithm for understanding how the deletions can eliminate sequence breaks. So let's see first how many sequence breaks there are in every sequence. How many sequence breaks are here? 1. Here, 1. Here, 1. In all these cases, there is just one sequence break required to break the sequence. How many sequence breaks here? 1, 2, and here 1, 2, and here 1, 2. What can we conclude from this? What's in common for 3, 4, and 5? And what's in common for 6, 7, and 8? The result of division by 3. All these, when divided by 3, give 1. 6, 7, and 8. Each of them divided by 3 gives 2. Exactly. The number of sequence breaks in a sequence is the length of the sequence divided by 3. As you can see, 9, 10, and 11 will have 3 sequence breaks. Okay? So number of sequence breaks in a sequence is the length divided by 3. But if we choose not to do replacements for the sequence break, if we choose to replace this method by deletions, how many deletions would it take? Let's do this. How many deletions would it take to eliminate just a single sequence break from each of these sequences? How many deletions to delete a single sequence break here, meaning to go from one sequence break to 0, 1 deletion. Here to go from one sequence break to 0 sequence breaks, 2 deletions. And here, 3 deletions. How about here? In 6, lengths of 6, how many deletions to go from 2 sequence breaks to just 1, to eliminate 1 sequence break? 1 deletion. How many deletions in a sequence of length 7? To eliminate a single sequence break, to go from 2 to 1. 2 deletions. And in 8, 3 deletions. What's in common here? What's in common for 3 and 6? In each case, it took 1 deletion to eliminate 1 sequence break. What's common for 3 and 6? Modulo 3 gives 0. Correct. What's in common for 4 and 7? Where deleting 2 characters eliminated 1 sequence break. Both 4 and 7, modulo 3 gives 1. 5 and 8, 3 deletions. Here to go from 1 to 0 and here from 2 to 1. So what's in common to 5 and 8? Yes, modulo 3 is 2. Conclusion. Number of deletions to eliminate a single sequence break is the length of the sequence modulo 3. If it's 0, it's 1 deletion. If it's 1, it's 2 deletions. If it's 2, it's 3 deletions. After the deletions, what are we remained with? We are remained with the maximum length of the previous level of division by 3. From all these, we got to 5. From 9, 10, and 11, all the deletions, in 9, how many would we need to delete? If the length is 9, then modulo 3 is 0, right? We'll delete 1 to get to 8. From 10 we delete 2 and get to 8. From 11 we delete 3 and get to 8. And in 8 there are 2 sequence breaks, right? So every time it gets us to the highest of the previous level of deletion dividing by 3. So, conclusion. In each sequence, we understand the number of sequence breaks of it by dividing the length by 3. Then, we do modulo of that length by 3. And that tells us how many deletions are required to eliminate just a single sequence break from it. How many deletions? After those deletions, in all cases, to remove all the rest of the sequences, we will need 3 deletions. 1, 2, 3. 1, 2, 3. 1, 2, 3. Just like we had here at 5. Okay? In all situations, after the first elimination of a sequence break, by deleting 1 or 2, all the rest will require deleting 3, because that's the highest level, the highest length of the previous level of division by 3. So this is what we're going to calculate. We're going to calculate all here in passwords that are too long. We're going to see how many extras we need to delete. Then we're going to see how many sequence breaks can be eliminated using deletions. How will we do that? Well, of course, we'll first check how many deletions of just one can break a sequence. So we'll see how many sequences modulo 3 length modulo 3 gives us 0, because that means that by just deleting one character from those sequences, we eliminated a sequence break already. 2 fixes in one step. If we will still have extra characters to delete, if it will still be too long, then we will see how many sequence breaks can be eliminated by deleting 2 characters, meaning how many sequences have a length where the modulo 3 gives us 1. After doing those deletions, if we still have extra characters to delete, if it's still too long, then we'll delete in chunks of 3. 3 deletions will eliminate a single sequence break. So by doing all those calculations, we can know how many sequence breaks can be saved, can be eliminated by the deletions. That number will go in the maximum with the missing types, as we do for a password of a good length after all the deletions. Okay? I think we're ready to write the code. So what you see here is a very long main, a main with lots of test cases, because I kept getting it wrong until understanding what I need to do. Okay, so let's write the code. So this is the signature from LeetCode. First, let's take the length of the password, as we're gonna need it many times. Let's declare booleans for the mandatory types. It will become true once we find a lower in the password. And digit. Let's declare variables for the calculations that we have just spoken about. How many sequence breaks are going to be required? How many deletions of a single character will eliminate one sequence break? And how many 2 characters chunks deleted will eliminate a single sequence break? Let's iterate the password and analyze everything. Okay. Let's check if the character at index I is one of the mandatory types. I can ask here if not lower found and this, but since this is a macro, it's very quick, so I'm okay just like this. And last, okay, so we have checked if the character is any of the mandatory type. Let's see if this character is the beginning of a sequence. let's calculate the length of the sequence. So I'm going to save the start point, and I'm going to move I until the end of the sequence. In the sequence, I'm gonna be in range of the sequence, not after it. So while I is smaller than n minus 1, because I'm going to look at the next character. Next character. I'm doing it because I increment I here, so I want to remain in range of the sequence, so that the plus plus brings us to after this sequence. So let's take the length of this. Plus 1, because both I and start are in range. Let's see if it's too long. If so, let's analyze. Let's add the number of sequence breaks that we have to do in it. 2 sequence breaks. And as we know, it's the length divided by 3. And let's see if the first sequence break there can be eliminated by deleting just 1 or just 2 characters from it. So let's see the modulo. And check. Instead of doing an if, I'll just do this. So if it's divided by 3 with no reminder, if modulo is 0, like 3 or 6 or 9, a single deletion will eliminate 1 sequence break. And here I'm going to multiply this by 2 because I'm not counting the number of sequences that are like this. I'm counting the number of deletions. So del 2 is the number of deletions that will eliminate a single sequence break, which is actually the first sequence break in every sequence, where modulo 3 gives us 1. In all those sequences, 2 deletions will eliminate their first sequence break. Okay, this completes the analysis of the password. Now let's check how many of the types are missing. So 3 minus everything that we have found. So the missing types will be between 0 to 3 inclusive. Now let's check which one of the cases apply. Is this password too short, good length, or too long? If it's too short, then we already know that we just need to return the maximum between missing characters and missing type. So missing characters is 6 minus the length, and missing types. Correct? Now in this case, all this work was redundant, but since we are doing the entire analysis here just once, then okay, we just iterate once even if we don't use what we've done here. It's okay. Now, if the password is of good length, then we know that the algorithm is the maximum between missing types and number of sequence breaks that we have to do. Else, password is too long. Let's first find out how many extra characters there are. So this is the number of characters that we need to delete. What we will return, here in a minute we'll calculate how many sequence breaks can be eliminated by the deletions. But what are we going to return? We're going to return, as we said, the number of deletions. We cannot avoid that. And then we have a password of a good length in which we are calculating the maximum between sequence breaks and missing types, correct? So here now let's eliminate the number of sequence breaks by the deletions. So well, first we try to just delete one to eliminate sequence break. So we, of course, can only eliminate a sequence break if we have characters to delete. We can't eliminate more sequence breaks than the characters that we are going to delete, because we're taking the numbers we deleted plus sequence breaks. We can't have this number lowered by deletions that we are not doing. So we are going to limit ourselves to the number of deletions in our hand. So let's take the minimum between the deletions in our hand and single deletions that eliminate single sequence breaks. Now, if we have some more deletions in our hand, we can eliminate more. So let's see first if we have more deletions in our hands. So if the number of deletions is lower than or equal to the number of deletions that eliminated the single sequence break, we don't have any more to delete. So it's 0. But if we have more deletions in our hand, then how many can we delete? It's the minimum between the number we still have in our hand, which is this, and this, which is the number of characters we need to delete. Here, right? Chunks of 2 characters at a time. A chunk of 2 characters deleted together eliminates a single sequence break from a sequence like of length 4 or 7, correct? But all these deletions need to be divided by 2 because every chunk of 2 deletions eliminates a single sequence break. 2 characters deleted together, a single sequence break saved, eliminated, so divided by 2. And if after all this we still have deletions to do, extra characters, then let's see if we still have. We don't have any more, but if we do, then all the deletions we're doing, we can say that each 3 deletions, a chunk of 3, can eliminate a single sequence break, right? From 8 to 5, from 8 with 2 sequence break, 5 with 1 sequence break, or from 5 to 2, from 1 sequence break to 0. So now deletion of 3 together will eliminate a single sequence break. So let's take all the deletions we still have in our hand and divide this by 3. So this is the number of sequence breaks we could just now eliminate. Now, sequence breaks can go to under 0 here. It doesn't matter, because when we do maximum between sequence breaks and missing types, this can be minimum 0, right? Missing type cannot be lower than 0. So maximum between them, even if this is below 0, maximum here will be 0. So it's okay. So it's okay if sequence breaks go below 0. I don't need to check it. So after all these deletions that eliminated sequence breaks, we return the number of deletions plus the maximum between remaining sequence breaks and missing types, as we know, for a password of good length. Let's see if this works. Before running it on LeetCode, let's talk about the complexity. So what is the time complexity? We iterate the password and that's it. So it's just O of n. And what's the space complexity? Well, it's just O of 1. We're not having any container or nothing. Let's copy this to LeetCode. Try to run it and try to not have Murphy law that will make it run too slow. Great. So it's 100% and space is also good. Time is more important. And that's it. So I hope you enjoyed it. And an important thing to take from here is to see that the description says, don't fix it. Just tell us the number of steps. I hope you enjoyed it. Thank you for joining me on CPP in Pajamas. See you next time.